Welcome to Math 106, Chapter 3.3, Related Rates Continued. So this is an optional video, but it does kind of help you with your homework. If an equation isn't specifically given, but perhaps more of a word problem, kind of mapping it out in our mind. So we'll go over two that are going to be seen on your homework. So it says a 10-foot ladder leaning against a wall is shown in the figure below. And it tells us right here in our problem that we need to use the Pythagorean theorem to find an equation for relating x and y. So it's nice. I won't exactly tell you exactly what to do on our test. However, we have it on this sheet. Now, the first thing we need to do is draw a picture. So some sort of a ladder, which is a 10-foot ladder, is leaning against a wall. So we have a wall here, which is shown in the figure below. And we have your ground. And if we relate this kind of in our coordinates plane, right, we can have our ground as an x and your wall being a height as in y. And we are going to be working with a right triangle, which the Pythagorean theorem helps us create an equation with your right triangle. So you guys should remember the Pythagorean theorem from perhaps high school, which says that we have a squared plus b squared is equal to c squared, which a and b are talking about your lengths here of your leg, and c is always going to be your hypotenuse. Now, in the context of our problem, though, we're not using a and b, we're using x and y. So we really should have x squared plus y squared. And instead of c squared, we know how long your hypotenuse is. That would be our ladder. So we have 10 squared here. Now let's simplify that ever so slightly. We have x squared plus y squared is equal to 100. And just like that, we have created an equation relating x and y together. Now let's take a moment to derive your equation, because we know that we will end up deriving at some point, because what we're going to be asked for is in part B, it says if the foot of the ladder, so if the very base of the ladder is being pulled along the ground at a rate of 3 feet per second, how fast, and it should say how fast is the top end of the ladder. So how fast is this portion of the ladder sliding down the wall at a time when the foot of the ladder is 8 feet from the wall? Now, before we dissect this problem, let's take a moment to derive your following equation. So if we have x squared plus y squared is equal to 100. Now we know we have the third variable. When we start to bring in some sort of a time aspect into play, right? We see two variables here, but there is that hidden third one where we're now talking about time, seconds. So when we go to derive, when we derive your x, where you said, okay, derive it as normal, right? 2x. Now, when we finished deriving, we needed to tack on dx dt, t being that third hidden variable that we don't explicitly see, plus derive y as normal, 2y. When you're done deriving your y, we get to tack on dy dt is equal to the derivative of a constant, 0. So right here we have dy dt, dx dt, and all of that. Now, let's go ahead and figure out, well, what are we going to be solving for? So let's pick apart your problem. It says the foot of the ladder is being pulled along the ground at a rate of 3 feet per second. Now, when it says at a rate, right, rate is always talking about the derivative. So we know that we either have a dx dt or a dy dt. Now, based on the context, the ground, looking at our picture, is that going to be related to an x figure or a y figure? Well, the ground being here, that is going to be related to x. So they really gave us dx dt. They said that is 3 feet per second. And it says, how fast is the top end of the ladder? The top end of the ladder sliding down the wall at the time. So we're asked to find dy dt. So we don't know what dy dt is. So we're going to have to solve for dy dt. They go on to say, though, that we're sliding down at the wall when the foot of the ladder is 8 feet from the wall. So the foot of the ladder here is 8 feet from the wall. So right there, they tell us that x is equal to 8. Now, what happened to your y? Because so far, if I were to plug these in, I have an x, I have dx dt, I am solving for dy dt, but I don't know what y is. So if y is missing, how do we figure out what is y? Well, you have lots of equations. Which one will give you the position of y? Well, the one up here will give you the position of y. You know what x is. You now need to figure out what is y. So to find y, plug in x to the original equation. Always, we do that time and time again. So if we have x squared plus y squared is equal to 100, right? You know that x is 8 plus y squared is equal to 100. So you have 64 plus y squared is equal to 100. Bring 64 to the other side. Y squared is equal to 100 minus 64. So y squared is equal to 36. Now let's go ahead and just get y alone. So square root both sides. Keep in mind, every time you create your own square root, we have to account for both the positive and the negative half. But because we're talking about some sort of a distance, some sort of a unit of measure, we're not going to be using the negative counterpart. So our answer will come out to just be positive 6. So now we have y is equal to positive 6. Now, at this point in time, if we want to substitute everything in here, that is perfectly fine. I'm probably going to solve it all the way as we're used to in our previous lecture, right? But let's go ahead and solve for dy dt. So I'm going to bring everything to the other side. That does not have the dy dt. So I'm going to subtract and then divide. So we now know that dy dt is equal to negative x, right? Reducing those 2's, we don't need the 2. Negative x over y times dx dt. And again, let's go ahead and plug in what we know. So we know that x is an 8. We know y is 6. We also know that dx dt is equal to 3. Let's go ahead and simplify here. So we'll leave behind a 2 on the bottom. So we get negative 4. Now, units here, we're talking about, right, feet, right? Your ladder is in feet. We're also sliding down the wall in seconds. So we have feet per second. Now, when we talk about what this actually means, right, we are trying to figure out how fast is the top end of the ladder sliding down the wall, right? If it's sliding in a downwards motion, we should have a negative value. So we could say something that the rate in which the ladder is falling or sliding down the wall is 4 feet per second. You do not need to say it's negative because you implied that it is falling here. So let's see this one again. So see if you can pause the video and try these ones out for yourself. I'll show all of my questions here. So it says an airplane flying 390 feet per second at an altitude of 5,000 feet flew directly over a radar station. The figure below shows the relationship between the airplane to the radar station at a later time. Now, this was supposed to have a visual aspect to it, but I think I eliminated that so that you guys could go ahead and draw it. So see if you can draw this relationship. So if we have some sort of an airplane, all right, we'll put that airplane over there. And we are flying over a radar station. Let's say the radar station is right here. We'll just do that. And we said, okay, we are 5,000 feet in the air. This airplane. And we are pinging it over. So you have 5,000 feet in the air, I believe. Yep, feet. 5,000 feet in the air. So this is your constant. This is your altitude. That's how your airplane is going to be flying. And we are looking at this can be your X. And for the sake of ours, we're just going to say Y is going to be your hypotenuse. And your airplane is going to be flying pretty fast, right? It's flying 390 feet per second at that particular altitude. Now, this Y is really the distance from the airplane to the tower. Now, I did not draw my airplane up above here because then it would just be a straight line, but we are motioning, we are flying as fast as can be. And so we are traveling away from this radar tower. So can you create an equation based on what we're seeing here? Well, again, it is a right triangle, so we could use the Pythagorean theorem. In our case, we can just say x is still just itself, x squared. Your b in our case is your other leg. This would be 5,000. And your c in our case is just going to be representing your y here, the distance from the plane to the tower. Now, part B says find the value of x when y is 13,000 feet. So they tell us that y is equal to 13,000. So we need to figure out, well, what is x? Well, we do know that we have your equation here, and we know what y is. So we can go ahead and plug that in. Solving for x, let's bring x over to the other side. Or sorry, your 5,000 to the other side. And we can go ahead and square root it. Keep in mind, every time we go to square root, we have that plus or minus sign. Taking the square root of 13,000 squared minus 5,000 squared, we end up with 12,000 feet. Now, our answer should come out as the positive half of it because we are talking about a distance, a unit of measure. So far, we now have your x, which is 12,000 feet, your y, which is 13,000 feet. Now, what else did we get? So at the very beginning, look at the very first sentence. It says an airplane is flying 390 feet per second at an altitude of 5,000. So is that going to be dx dt or dy dt? Well, that should be dx dt. This is 390 feet per second. It's changing at that particular rate. So in C, it says how fast is the distance from the radar station to the airplane changing at that time? So we want to know how fast is this distance changing? So we are looking for dy dt. We don't know what that is. So can we go ahead and find that, that measure? So if we know that we have x squared plus 5,000 squared is equal to y squared, we now need to put in dy dt, dx dt. So in other words, we need to go ahead and derive. let's go ahead and solve. So dy dt is equal to x over y dx dt. When we know that x is equal to 12,000, y is equal to 13,000, and dx dt is equal to 390. So let's go ahead and put that in. So we have 12,000, 13,000, and 390. Our zeros can make it a little bit easier. And if we were to plug that into your calculator, we have 12 times 390 divided by 13. So we should get 360. And again, units on here is feet per second. So how fast is our distance changing? So how fast is the distance from the airplane to the radar station changing at a rate of time? We have 360 feet per second. So hopefully that clarifies kind of these related rates, the visual aspect of it, trying to figure out, okay, what do we do if we have more missing values, but creating an equation.